going to say lower bound. What is definition of the lower bound? Definition. Let S is an ordered set and A subset S if there is beta belongs to S such that beta less than equal to x for all x belongs to A, then we say that A is bounded below and beta is lower bound of A, right? Okay. Then there will be many lower bound of the set A. Let's look at simple example. Let us consider the open interval 0, 1. Here 0 is the lower bound of the interval j equal to 0, 1. 0 LUB of j, right? If beta will be lower bound, then beta must be less than equal to 0. Okay? Have you understood? Therefore 0 is the greatest lower bound of the set G. Now I want to say what is the greatest lower bound? Let's see. Let's see the definition of greatest lower bound. Suppose S is an ordered set and A subset S and A is bounded below. Suppose there exists and beta belongs to S with following property. With following properties. One, beta is a lower bound of A. 2, if delta greater than B, then delta is not a lower bound of A. Okay? Then beta is known as greatest lower bound. Greatest lower bound of A, or we can say it infimum of A, right? And we denote it as beta equal to infimum of A, right? Okay. Let's see some properties of LUV. Let A be any non-empty set and let gamma equal to GLB of A and delta equal to GLB of P. Let's look the picture. This is B and this is A. Have you understood this? Now let us see simple example. This is 110 and this is 57. This is the subset A and this is B. What will be GLB of B? GLB of B is 1 and GLB of A is 5. That means GLB of B less than equal to GLB of A. Now we want to prove it, and the proof is very easy. That means we want to prove delta less than equal to gamma. We know for all x belongs to A imply x belongs to B also. That means x greater than equal to delta. That imply delta is a lower bound of A. Okay? But what is gamma? Gamma is the greatest lower bound of A, right? And delta is the lower bound. So gamma must be greater than equal to delta. Have you understood it? That means GLB of A greater than equal to GLB of B. This is my proof. And in my previous video I have proved any non-empty set A which contain B, then LUB of A less than equal to LUB of B. This is the relation of LUB and GLB. Now I am going to say some properties of upper bound and lower bound. Let alpha is an upper bound of A and beta is an upper bound of B. Then what is the upper bound of A union B? The upper bound of A union B is max of alpha beta, is the upper bound of A union B, and I want to prove it. Okay, let us denote gamma equal to maximum of alpha beta. Then what is relation of alpha, beta, gamma? Alpha must be less than equal to gamma and beta must be less than equal to gamma. Then I want to prove gamma is a upper bound of A union B. That means for all x belongs to A union B, x less than equal to gamma, right? Let x belongs to A union B. What it implies? X may be either A or x may be in B. Case 1, x may be A. That means x less than equal to alpha, alpha less than equal to gamma. Case 2, x belongs to B. That means x less than equal to beta, also beta less than equal to gamma. Therefore, gamma is an upper bound of A union B. Have you understood it? Okay. Now, alpha equal to lower bound of A and beta equal to lower bound of B. Can you construct lower bound of A union B in terms of alpha beta? I leave it for my viewers, and this is easy. This is same as this. Just think it. I leave it exercise for my viewers. Okay. Now I want to show some observation of real life. Observation. Real line has lower bound, real line has least upper bound property if and only if real line has GLB property. Let alpha equal to LUB of A, then minus alpha is GLB of minus A. This is A, this is minus A. Okay? Since alpha is LUB of A, then for all x belongs to A, imply x less than equal to alpha. That imply for all x belongs to A, minus x greater than equal to minus alpha. Therefore, minus alpha is an upper bound of minus A. Let beta is lower bound of minus A. Then for all x belongs to A, imply minus x greater than equal to B. That imply x less than equal to minus B. Therefore, minus B is an upper bound of A. Therefore, what is the relation of alpha and minus B? Alpha less than equal to minus beta. That imply minus alpha greater than equal to beta. Therefore, if alpha is lower bound of A, then minus alpha is GLB of minus A. Therefore, alpha equal to LUB of A, then minus alpha equal to GLB of minus A. Okay. Now conversely, if lambda equal to GLB of minus A, that imply minus lambda equal to LUB of A. This is the converse proof, and the proof is similar. So I leave it for my viewers. Just try it. Now look at new topic Q and R. We know algebraic property with respect to addition and multiplication is same in both Q and R. Similarly, order property is same, but only R has LUB property. Q does not have any LUB property. Okay? Why? Just think. Let us consider the subset E equal to set of all rational number Q belongs to Q such that Q square less than 2. This is subset of Q. Have you understood it? Okay. clearly E is non-empty because 0 belongs to E. This is E. And every number E is smaller than 2. If Q was least upper bound axiom, then the supremum of E equal to square root of 2, which is not a rational number. So, supremum does not belongs to the subset Q. So, Q does not have any least upper bound. Have you understood? Right? Okay. LUB property is concept of real analysis. All theorem depends on this LUB property. Now, I am going to say another topic of LUB property. Let's give an example. Let's give me an example. A subset of R which is not bounded above in R. Can you think? What is this? This is natural number. Why? Let's root the real line. 0, 1, 2, 3. This is n. Let alpha be least upper bound. Then alpha minus 1 is not upper bound. Is not upper bound. That means there exists a not belongs to natural number such that alpha minus 1 strictly less than n naught. That imply alpha less than n naught plus 1 and n naught plus 1 belongs to natural number. This contradicts alpha is the least upper bound. So, natural number does not have any upper bound. But natural number have least upper bound in Q. Think it. It is very easy. N is not bounded above in R, but N is bounded below in R. 1 is greatest lower bound, right? Let's look at Z. N contains Z. Z is not bounded above because any upper bound of Z also upper bound of N, but N has not upper bound, though, so Z is not bounded above, right? Next, is it bounded below? Is it bounded below? Let's look the picture. This is 0, this is -1, this is -2, this is -n. If alpha is greatest lower bound, then there exists -n which belongs to Z. This is not possible. So Z cannot be bounded above. Have you understood? Right? Okay. Bye. Next video I will discuss Archimedean property of R.